Hi, Nancy.
Hi, Shane. That was so... Hi, Nancy. Like, this is the most painful part of the day right here.
Oh, goodness. Oh, no. All right, let's bring it up. I have a question for you. Let's pretend that you are you have to go into a fallout shelter for Thing Explorer. Yeah, we're just diving into it. Like, there's no pretense anymore. What is something that you would want to take with you to stay entertained for, God, weeks,
I can answer this for
months,
Nancy.
years. Oh, and Lauren's
really?
here
You
too.
could?
Books.
Well, definitely books, but I guess more specifically, like, what book?
Yeah, what book?
Or like 90210 episodes. But
Yeah.
what about if you were watching? You could bring some episodes of that show Chernobyl. Like, it would be like real meta.
Welcome to the American Geophysical Union's podcast about the scientists and the methods behind the science. These are the stories you won't read in a manuscript or hear in a lecture. I'm Shane Hanlon.
And I'm Nancy Bompey.
And this is Third Pod from the Sun, Centennial Edition.
So it turns out that here on Third Pod from the Sun, we happen to love the Cold War. I mean,
it.
We really do.
It is interesting. They're just some interesting stories. So I actually interviewed a scientist, Caroline Clason, who studies glacier melt at the University of Plymouth in the UK. But for some reason, my memory of this is vague.
Nice.
No, Lauren helped me with putting this episode together as well. So I'm going to bring in Lauren LaPuma, who is our in-house Cold War climate change nuclear expert.
Yeah, she's Jane of all
Explain
trades.
what this is all about.
I'm basically a Cold War historian at this point.
Yeah, yes.
So, as we talked about on this show before, so there was a lot of nuclear weapons testing going on in the atmosphere for about at least 20 years, starting after World War II ended. Mostly the U.S. and the Soviet Union, but some other people too, detonated hundreds of bombs in the atmosphere. And of course, all that led to a lot of fallout. There was a test ban treaty that went into effect in the 60s, but there was still a little bit of atmospheric testing that went on after that. But then, I don't know if you remember, Nancy, you might have been the only one of us here that was alive during Chernobyl.
I don't remember that.
But you were very little. Right. Then we had that nuclear disaster at Chernobyl where the power plant melted down during a safety test. The reactor core exploded, and all this fallout traveled over Russia and Europe for 9 days until it was contained. It was really bad. And so what Caroline is studying now is that fallout is actually on some glaciers. So this is a big surprise and bad discovery that scientists found.
Yeah, and it could be a big problem, obviously.
I'm Caroline Clason. I'm a lecturer in physical geography at the University of Plymouth, and I'm also a glaciologist. Yeah.
All right. So today we're at the European Geosciences Union General Assembly, and you talked a little bit about the research that you're doing. Can you tell us a little bit about that?
Yeah, sure. So what I've been presenting this week at EGU is emerging research on the presence of something called fallout radionuclides in a sediment called cryoconite, which is stored on the surface of glaciers. So cryoconite is a sediment that you find, it's a very dark sediment that you'll see quite easily on the surface of things like the Greenland ice sheet and alpine glaciers. It's composed of some organic material and some inorganic material, so rock and mineral matter. It could have black carbon from the atmosphere, but also life. So cryoconite holes are hotspots of biodiversity. So lots of glaciologists are interested in cryoconite from a life perspective, actually looking at what's in it. It also contains plant matter, fungus, that kind of thing too.
So kind of everything that lands on the glacier?
Yeah, basically.
Yeah.
So especially when they form these holes on the surface, the reason you have these holes is because the material is darker than the surrounding ice, so it absorbs the solar radiation and it melts faster. So that means that they're little buckets, I guess, if you like, that can trap everything that falls onto the ice surface. So they're a real hodgepodge of different materials. And while people have studied things like carbon and nitrogen being stored in cryoconite and shown that it was quite efficient at actually absorbing that, no one had really focused until quite recently on the presence of contaminants specifically in this material. So our study that we've been presenting this week is about these fallout radionuclides from nuclear weapons testing and accidents like Chernobyl, and how they've actually been accumulated over decades in glaciers, particularly in this sediment. Yeah.
So you found, like you said, these radionuclides in the cryoconite, but how are they getting there?
When there is a nuclear accident or a weapons test, a lot of those, the materials produced by these incidents end up in the atmosphere. So when they're in the atmosphere, they're then interacting with precipitation. So in other sort of terrestrial environments, they're brought back down to Earth, if you like, through interaction with rain typically, and they end up quite distributed across the environment. On glaciers and in high latitude and high elevation areas, a lot of precipitation obviously falls as snow, and snow is a really efficient scavenger of particulates from the atmosphere. So they're sort of attracted to the snow. And then the snow falls on top of the glaciers, turns to ice over time, and they end up stored in those glacier systems. So they're concentrated initially through that interaction with the snow and ice. And then as the glaciers melt in response to climate, that meltwater then comes into contact with the cryoconite on the surface. And as it runs through these cryoconite holes, it actually allows that to accumulate in the sediment. Yeah.
So what are these radionuclides, and like what do they have? I guess, do you know kind of what they can do or how harmful they might be to people? Or
yeah. So one in particular called americium-241, it's a decay product of plutonium-241, which was produced obviously through things like Chernobyl. Plutonium has a half-life of 14 years. So that means that it's already decayed quite rapidly since its deposition a few decades ago. Americium is a product of that decay, and americium has a half-life of over 400 years. So once it gets into the environment, it's going to stay there for quite a long time without decaying. Americium is an alpha emitter, and alpha particles, although they're stopped much more easily than things like beta and gamma that require metal and lead to stop the gamma rays. Alpha is quite dangerous if ingested, basically. If it's eaten or maybe if you breathe it in, at that point it can then potentially be taken up into humans, but mainly the concern is over grazing animals in this case that are living in the proglacial environment or directly downstream of glaciers. So that's where the real concern is. Cesium, which is another one of these artificial radionuclides, it's the big one. It was heavily reported after Chernobyl, the presence of cesium in the environment, really big issues in parts of even the UK. For hill sheep farming, for example, there was a lot of meat that just wasn't able to be sold. And obviously in parts of the further north where reindeer and elk are an important part of the economy. So cesium is still an issue, although it's actually it's half what it was after Chernobyl, because its half-life is about 30 years.
Okay.
So it's already decreasing, but the levels are still huge in what we see in the cryoconite, and orders of magnitude above what we see in the downstream environment.
So the stuff from Chernobyl then has it's been in there since the accident? I mean, I guess it was 86, right? So
Yeah.
It's been in there basically on the glaciers since that time, and now it's starting to melt off?
Yeah, so probably the biggest spike in deposition would have been at the time, although there's obviously some still kind of kept in the atmosphere and circulates around, so it's deposited for a little bit longer. And we can see that, and we took a lake core sample as well, and we can actually see these really clear spikes from things like Chernobyl, or a spike from around 1963 from nuclear weapons testing when there was a lot of testing going on. So when you take these lake cores and split them up into sections and run those, not so much to look at contamination levels, but to actually date the sediments, and you can see them really clearly in the sediments in the lake just downstream of the glacier. So the highest source is definitely kind of almost directly after these events happen. Yeah.
Were you surprised that you were seeing this? I mean, that these high levels? I mean, was that surprising to you when you actually, ended up running these? I guess, did you go back to the lab and run the tests?
Yeah. So I've had to learn a lot of lab techniques. I've never been a lab scientist before. I was a glaciologist, still am really. But yeah, so I'm learning a little bit about geochemistry these days. You take it back to the lab. We have a lab in Plymouth that has what we call a gamma spectrometer. And that works by placing your sample into this detector, and it measures the spectrum of gamma radiation emitted by each of those samples. And by looking at the sort of peaks in that spectrum, you can see how much of each different radionuclide we have in the sample, whether that's natural radiation or artificial radiation. Yeah.
So when you saw those spikes, I mean, were you like, oh my God, this is scary?
I was surprised, yeah, especially, I mean, I'd seen a paper that was, from the Austrian Alps, and we knew that the levels there were high, but it's also quite close to Chernobyl, relatively speaking. So when we looked in Arctic Sweden, and I went there because actually it's just one of my favourite places to be, and I'd worked in that environment before, and I knew I could access the ice, and So I was really surprised that actually some of the highest concentrations we've measured in all of this ice are up there in Arctic Sweden. That could be down to atmospheric circulation. It could be down to just being a really high organic content in the samples there. But for some reason, the concentrations are very, very high up in the Arctic.
Are you seeing the fallout from Chernobyl, I mean, very, very far away from the site? Or you see it, yeah, obviously it's closer, I guess the closer you are, perhaps you see different concentrations, but...
Yeah, it's hard sometimes to tell exactly whether the main source is Chernobyl or whether it's weapons testing. So you can look at the ratio between different fallout radionuclides to give you an idea of what the source might be. But actually what we're seeing is an accumulation of fallout radionuclides over a period of decades. So it's being built up not just from Chernobyl but from other sources as well. So it can be hard to pick that apart. But definitely we see the highest values closest to certainly Chernobyl, so the alpine samples are all quite high. But also in Svalbard, because there was nuclear weapons testing up in Arctic Russia, and we also see quite high levels up there as well in the Arctic, following on from those bomb tests probably. So it varies from site to site. And also, I mean, there was a lot of weapons testing in the Pacific Ocean as well, on the atolls there. What we don't have yet is samples from South America. So that's one of my goals for this summer is to go, I'm doing a different project in the Peruvian Andes that starts this year. And I'm going to make the most of being out there to get some samples and actually look and see whether you can see the signal of those weapons tests from in the Pacific, in the Southern Hemisphere.
But so far, like you said, in all the samples you've taken, there's some indication that of something in these samples.
Every single sample that's been analysed has had artificial and natural radionuclides. So there is global reach, whether that's Chernobyl or whether that's in other areas, maybe more heavily related to weapons testing or other nuclear accidents. But even our furthest south samples from the South Shetland Islands off the coast of the West Antarctic Peninsula, and there's even radioactivity, anthropogenic radioactivity, as far south as that. I mean, these are like relatively pristine environments. You know, they're becoming less pristine, obviously, because we go there, we take tourists there, you know. But to think about the reach of anthropogenic contaminants like this, and radioactivity is one thing. We're also looking at heavy metals and other elements as well, because it's important to look at the sort of whole spectrum of stuff that we're putting into the environment.
Yeah, so what's happening to them? So when the glaciers are melting now, what's happening to this stuff?
Yeah, so some of it, or eventually all of it, will find its way into what we call the proglacial environment, the environment in front of the ice. So it's very light. Cryoconite is, because it's so organic, it's a really light sediment, so it can be mobilized quite easily in meltwater. So some of that will be washed downstream under melting. But also if the ice decays, sometimes glaciers just thin rapidly because they're undergoing so much melting. And if that happens, cryoconite could potentially be just deposited onto the land surface underneath as the ice decays and retreats. But largely it's through interaction with meltwater and being washed down into the river system downstream. And because the glaciers are retreating more and more, they're melting more and more, and that just means that more of this material is being mobilized over time than would have happened, 30 years ago when climate wasn't quite as warm as it is now.
So when it gets into the water then, what happens to it? I mean, what happens to it? Are we going to drink it? Are animals going to,
So that's the concern. And I think we don't know completely what's happening there yet. That's kind of the next step of the research really, is to look at how likely it is to be taken up into the food chain. So our worry is that if we compare things like lichens and mosses in the terrestrial environment that people have been looking at since Chernobyl in particular, they are also quite efficient at scavenging contaminants from the atmosphere. So levels of things like fallout radionuclides are typically higher in fungus and mosses and lichens than they are just on grasslands, for example. So when wild boar come along and eat those things, that can pass into the meat. And in Sweden, the government there currently has a scheme where they're actually testing wild boar meat even now, because they're finding samples that are an order of magnitude higher than the legal level for selling meat. So it's a contemporary issue still. But that's in the terrestrial environment, like off ice. The levels in kryokonite are higher than what have been found in a lot of these mosses and lichens. So when that material does make its way downstream, there's potential that it might actually be more harmful. But we have to remember that the absolute volume of kryokonite in the environment is quite small in comparison to other types of sediments. So actually, when it makes its way downstream, it's probably going to become quite distributed. And it's the extent to which they stay kind of clumped together and are just deposited on the land surface, or whether they're washed away with water and become much lower concentration material. So I think that's something we really need to be looking at in the future. So we're now trying to build socioeconomic impact into that, and maybe think about approaching some of the people that live and rely on those environments. So the Sami, for example, in Arctic Sweden, who rely heavily on reindeer herding for their livelihoods and for culture as well. So something we would like to do is actually go and talk to them about the extent to which they realise there's any of these issues in the environment. I'm sure they're really vividly aware of the impact of Chernobyl, because 30 years ago that had a huge impact on their livelihoods. But I think it is important that we flag this as a potential issue. We don't know the extent to which the hazard is big here, because we haven't assessed how easily this can be taken up in the food chain yet. But we are looking into that, and that's something we'll develop in the future.
When you're trying to figure out long-term how the nucleotides are going to impact the food chain and actually get into animals and people's systems, is there a way to predict, based on like the velocity of the glaciers, how long things are going to take to end up in the proglacial environment? Or is that part of it? Or
yeah, so to some extent we have a bit of a grasp already on how quickly sediments can make their way through the system. So if you extract a lake core from the proglacial environment, you can actually look at sedimentation rates. And that's sediment that's come from underneath the ice, on top of the ice, and is washed downstream over the course of the melt season. And that builds up year after year. So we can take those cores and actually see how materials are being moved downstream, sort of almost in real time, if you like. Just in the previous years, you can go back and directly look at what was deposited a few years before, right back to 100 years or so, or more maybe. Although we're not 100% sure what the impact of this will be yet. I do have a student at the moment working on something called sequential extraction, which is taking some of my kryokonite samples that I've collected in Sweden and Iceland, and she will be sort of putting those samples into solutions of stronger acidity over time to try and see if the particles are sort of bound to the really organic content. So if the fallout radionuclides are being bioaccumulated in that organic content, they'll be released quite easily. So that could even be through interaction with water. Testing acidic concentrations, so actually putting the samples into something that might mimic stomach acid to see if it's then released into the food chain that way. And then every time you do that, you put the sample back into the gamma detector and see what's left, if anything. So you can split the components. So we're really interested. We know it's there. We know it's in the environment. We know it's global. But I think now's the time that we have to now look at process, both in terms of how it's accumulating physically in the first place, and then how it's being taken up into the rest of the environment.
So I guess the question is, like, they don't know everything, right? They just have to wait almost to see, is climate change going to be the thing? Like, they have to wait for the glaciers to melt to see how bad it is.
No, I think it's that they haven't done the testing. Like they have to go through all those levels of animals, Mr. Biologist.
Hey, my podcasting hat is on right now, and my biologist hat is off. So,
well, maybe you should be the one doing this testing, Shane.
Why me? There's much more qualified people. I'm happy to sit here and talk about it.
I forgot. And you only study frogs.
Yes.
It doesn't matter.
So which is worse? The melting glaciers with the nuclear fallout on them, or we have the
or
Camp Century in Greenland with the waste buried underneath the ice sheet.
Well, there's radioactive waste there too.
That's what I'm saying. So
it's
all bad.
Radioactive. It's all bad. I wonder which one will kill us first.
Stay tuned for our new series on terrible things happening in the environment. But for now, that's all from Third Pod from the Sun.
Thanks so much to Caroline for sharing her work with us.
This episode was produced by Nancy and Lauren. Thanks, Nancy and Lauren. And mixed by Robin Murray and John Schreiner.
AGU would love to hear your thoughts. Please rate and review our podcast on Apple Podcasts. Get it wherever you get your podcast, or as you can always find it on thirdpodfromthesun.com.
All right, thanks all, and be on the lookout for more Centennial episodes to come.